Have you ever thought about how different the world looks at its absolute tiniest scale? Imagine trying to pinpoint something so small it behaves less like a tiny ball and more like a shimmer of possibility. It truly is a mind-bending idea. A quantum probability cloud is essentially a visual way to understand where an electron or other subatomic particle is most likely to be found around an atom. Instead of thinking of an electron as a tiny planet orbiting a sun, imagine it as a fuzzy, three-dimensional region where its presence is spread out like a cloud, indicating the odds of finding it at any given spot. The core reason for this cloud-like behavior stems from the wave-particle duality of quantum mechanics. Particles at this scale, such as electrons, do not have a fixed position until they are observed. Before observation, they exist as a wave function, which is a mathematical description of all their possible states and locations. The probability cloud you see is directly related to the square of this wave function. Where the cloud is densest, the probability of finding the electron there is highest. Where it is sparse, the probability is lower. To better grasp this, think about a fan blade that is spinning very fast. You cannot see the individual blades at any one moment, but you can see a blurry region where the blades could be. The denser part of that blurry region is where the blades spend most of their time. Similarly, electrons whiz around the nucleus at incredible speeds, and the probability cloud represents their potential locations over time. This concept is fundamental to understanding how atoms and how chemistry works. For example, the distinct shapes of these probability clouds, often called orbitals, determine the geometry of molecules and why certain elements react in specific ways. Scientists use complex equations to calculate these wave functions and predict the cloud shapes, which are then experimentally verified. Understanding the quantum probability cloud helps us move beyond simple planetary models of the atom. It reveals that the universe at its smallest is a place of inherent uncertainty and statistical likelihood, rather than absolute certainty. This probabilistic nature is a cornerstone of modern physics, guiding our understanding of materials, energy, and even the very fabric of reality.